So then in chapter 5, we applied all of Newton's laws to the motion that we got here. We introduced this idea of friction, that there's static friction and kinetic friction. We introduced this idea of drag forces, and the drag forces are resisting you as you move through the fluid. So as your velocity increases, your drag can increase, and it can increase by v or v squared depending on the scenario. We showed ways of deriving that and getting velocity as a function of time. You could be asked maybe to solve for acceleration as a function of time. Centripetal forces are the cause of you changing your motion. So we looked at bank curves, we looked at vertical circles, we looked at scenarios where whatever force is pointing in and in line with the center of the circle must be accounted for to give us our centripetal force. Centripetal force you can then just solve as F equals ma, and the acceleration is now your centripetal acceleration we used from before. So we talked about a bunch of different scenarios when you're swinging buckets over your head or going around loop-de-loops. Go back to those and know what the seat is doing versus what you are feeling. When you get to the top of the circle, you feel lighter because the seat doesn't push back on you as much. When you get to the bottom of the loop, the ground is pushing back up on you very hard to try and keep you in that circle. Your body just wants to do what it was last doing. It wants to head off in a straight line motion. And the last thing we put up in there is the center of mass. The center of mass was a way to analyze a scenario that has masses in all directions. If we focus on the center of mass, we can apply all our kinematics and forces to that center of mass and predict where that center of mass will move. The only new equation in chapter 5 was the friction equation, and the friction equation is fun, so it's mu times your normal force, and your normal force does not always equal mg. Look at your scenario and see what it matches up to. And in chapter 5, we introduced this idea of work and kinetic energy. Work, you must push on an object and move it through a displacement. So it is an integral, especially if that force is not constant, like spring forces. So we saw that when you do work on objects, what you do is you change an object's kinetic energy. And when you change your kinetic energy, you can use a force position graph to get the area under the curve. The area under the curve will equal the work, which will then correlate to how much speed you've gained in your scenario. Work is also a dot product, so remember the rules for dot product, and I.I, J.J, K.K, those are the only ones that actually work. Power is the work that you do over time, so it's a rate of energy transfer, and work done by friction is always fighting you and trying to decrease your energy of your system. So usually work done by friction is negative. The equations we came up with, we got the kinetic energy equation as 1/2 mv squared. We've got power as work over time, or it's the derivative of work over time if your force changes with time. If your force is nice and constant, then we have force dotted with velocity to give us our power. And then we moved on to chapter 7. We used that kinetic energy idea to then talk about conserving energy, and we talked about gravitational potential and elastic potential, new stored types of energy that you don't need to use, but you have the ability to use. We then looked at this idea of conservative versus non-conservative forces. Conservative forces are path independent. They only care about starts and finishes, like gravity and springs. Non-conservative forces, like someone applying a force, a frictional force, they care about where you actually move the object. So they will always add or maybe take away energy from your system. So then we conserved energy and looked at all the energy before a system and after a system. We graphed it out with the LOLs, and basically a way for you to write yourself conservation of energy equations. And we looked at we looked at energy position graphs. And we saw as energy changes with position, that's due to a force. It's actually the negative derivative of energy over position. And the reason it's negative is because usually we're dealing with conservative forces that will try and decrease your potential energy as quickly as possible. And the force will always push you back towards an equilibrium point. So new equations in this would be mgh for gravitational energy. The spring force is minus kx. And the energy in a spring, we took the integration of the force equation over a distance and ended up with 1/2 kx squared. So that x in the elastic energy there is the stretch in the spring, not the actual distance of the spring. They may give you that value. All you're looking for is the compression or stretch. And finally, we covered chapter 8. Is momentum conservation, and we got this new idea of momentum and impulse. So momentum is just simply mass times your velocity. The forces involved change your momentum with time. So really, force is the derivative of momentum over time. We talked about changing momentum, or this idea of impulse, and a change in momentum is equal to your force multiplied by time, or J, as you have on this equation sheet. So when momentum changes, an impulse has occurred, and that's all that means. And we analyzed a lot of different scenarios to figure out how we minimize the force during an impact, or how the collisions change your momentum if you know forces and times. We talked about different types of collisions in terms of elastic and inelastic collisions. Really, if you want to know the difference between them, elastic conserves kinetic energy and inelastic does not conserve kinetic energy. Perfectly inelastic is just when they hit and stick. Any collision, you can analyze momentum before and after. If the energies don't match up, then you're dealing with an inelastic scenario. And finally, we did collisions in 2 and 3 dimensions, and what we did with that is we looked at momentum in the x direction or the y direction, and we just made sure we conserved both. If you conserve momentum in all directions the whole way through, you'll be good to go. And that's what the coefficient of restitution was telling us there, that basically your recession speed should equal your approach speed. So whatever speed the two objects are coming towards each other at, they must also go away from each other at. So those are the topics for chapter 1 through 8. Good luck studying. Remember, we also have my entire video library that you can go back through and watch again, practice some old web assigns, go through your old homeworks, go through your notes. We'll see you on test day.